Hello everybody, and welcome back to another video. In this video, I will be covering Riemann sums. Now, a Riemann sum is an estimation for an area under a curve. So let's say you have a graph of velocity versus time. And you have a constant velocity of 3 meters per second that is applied over a time of 3 seconds, assuming both these are at 0 and 0. Now, we know that velocity is equal to d over t, and velocity is the rate of displacement. So what this means is that our rate is equal to our thing being measured, which we are going to just label with x over t, assuming that the rate is constant. However, in many cases, including the one that we are doing later today, the rate will not be constant. So for this problem, the graph just looks like this. So if we want to find the displacement traveled in 3 seconds, we can rearrange this formula by multiplying both sides by t, and we get d is equal to v times t. And if we look, this side of a rectangle that we could form, or in this case it's a square, is a velocity, and then this side is a time. So our displacement, or our x value, is equal to our rate times time when the rate is constant. However, when the rate is not constant, it's all of the, let's say that it's like this graph, it's all these infinitely many small rates and times added up. However, we cannot do it infinitely many times, so we are just going to be approximating. So in this case, it would be equal to 3 times 3. This is meters per second. This is seconds. So the seconds cancel out. And then you are left with x equals 9 meters. Now, we are going to be using a 1 second approximation for this problem, and we are going to be doing a right-hand sum. So what that means is that we are going to be making an approximation for the area under this graph, which is a fuel tank having liquid pumped into it. And we are going to be approximating the total amount of fluid pumped in by 5 seconds. So, in order to do this, we must find each of these areas, as these are our best ways of approximating this function's area. Now, since this is the height and this is the base, we know that each of these segments is just going to be the rate times the time. So for this first little segment here, this is going to be 1 second times, as you can see right here, this is 0.5 liters per second. So this first segment is equal to 0.5 liters. This segment right here is 2, or 1.5 times 1. So this is equal to 1.5 liters. And since all of these are multiplied by 1 second, we are just going to be skipping this step right here, as we will just get rid of the units per second for the height. Now this one right here is 3.5 liters per second times that 1 second. So it is 3.5 liters. Then for 4 seconds, we can see that this is equal to 5 seconds. So this is going to be 5 liters, 5 liters per second. So this is going to be 5 liters. And then for 5 seconds, it is a rectangle. This is actually not an approximation. This certain rectangle right here is just exactly equal to 1 second times the 5 liters per second. So this is plus 5 liters again. Now, adding all these up, we get our approximate area under the curve. However, this is not exact. As you could see at the top, there is extra area, so this is an over-approximation. However, it is still good for understanding, and the closer we put these points, the more accurate it will be. So our answer for our amount of gas pumped in over this time span is 15.5 liters. Now, this is only approximate. We know that we could have gotten a better assumption using this height right here and this height right here and doing a trapezoidal approximation where our formula for an area of a trapezoid is equal to base 1 plus base 2 over 2 times height. Now that would have given us a much more accurate area. However, in this case, we were just asked to do a right-hand sum. I hope you all understood and enjoyed this video, and thank you for watching. Please like and subscribe, and I'll see you in the next one.